Good morning. This is Professor Dixon in the Department of Chemistry. I'm going to tell you a little about the work of my research group today. Our efforts are in geosciences, heavy element chemistry, catalysis, and an Energy Frontier Research Center. These are who fund us from the Department of Energy Basic Sciences. And also we get funding from a DoD SBIR. What are the science drivers that drive the research in our group? Well, we do science across scales in space and time. We do work in catalysis using computational chemistry methods. We look at transition metal oxides, homogeneous catalysts, metal clusters, and single-site metal atom catalysts. We're very interested in energy applications, including the Advanced Fuel Cycle Initiative, looking at ways we can do metal oxide clusters in solution for new fuels for nuclear reactors, as well as environmental cleanup. And a lot of this involves heavy element chemistry, where we have to worry about the fact is that the electrons in heavy elements behave in a different way due to relativistic effects. We're very interested in looking at things like metal organic frameworks, ZIFs, COFs, and transition metal oxides for acid-gas separations. We also have work going on in geochemistry looking at geological CO2 sequestration and mineral formation and dissolution. In the environment, we're interested in looking at atmosphere, clean water, subsurface chemistry, and cleanup. In biochemistry, in collaboration with the Cassidy group here, we're looking at peptide and amino acid negative and positive ion chemistry. We do a lot of work in computational main group chemistry, for example, fluorine chemistry, looking at acids and bases, as well as other elements. We develop methods in computational thermodynamics and kinetics to get the highest accuracy possible. And then we're also looking at some experimental work in energy and looking at hydrogen storage and chemical systems, both organic and inorganic systems, for high velocity propulsion, as well as for fuel cells. As a cross-cut example of how these things come together, let's think about acid-base chemistry in the gas phase in an aqueous solution. For example, in catalysis, we're interested in looking at alcohol conversions, and that involves acids and bases, or looking at hydride transfer. And we were interested in looking at strong acids for catalytic conversions. In biomass conversion, much of what we're looking at are involving organic alcohols and acids. In heavy element chemistry, we're interested in looking at the control of oxidation and oleation reactions, basically whether we're going to form metal oxygen or metal hydroxide bonds that lead to condensation products and things like colloids in aqueous solution. Obviously, the anion proteomics involves acid-base chemistry. Our chemical hydrogen storage, we're looking at protic-hydritic interactions to lower potential energy barriers. And then we're looking actually at degradation of MOFs and ZIFs by acid and bronzite gases. And so when we talk about acid-base chemistry here, we're talking about both proton chemistry as well as looking at Lewis base and acid-base chemistry. We're interested in chemical accuracy, what's needed for chemical accuracy. We want to be able to predict equilibrium chemistry reliably in order to do selectivity. So a change in a rate constant, a factor of 10 at room temperature, is about a change in delta G of about 1.4 kcals per mole. That's also 1 pK unit. If we want to look at absolute rates, then a factor of 10 at room temperature is about a change in activation of 1.4 kcals. How do we do this? Using quantum chemistry. Another question we have to address is what are the correct physical models that we want to try and use to make these predictions. Some issues we have. What are the uncertainty in the models that we're using? What are the errors in the calculation of experiments? And how do I maintain accuracy across a wide range of length scales from molecular all the way up to the macro scale? And then again, as we have errors, how do we incorporate error bars in our simulations to know that we're getting the right answer? The computational methods we have range from correlated molecular orbital methods through density functional theory all the way up to molecular mechanics. We tend to focus on the most accurate methods at the top. And on the right, I just show you the different Nobel Prizes in theoretical chemistry, although not all of them are in chemistry, but you can see that this area has been very important in advancing chemical sciences. Let me give a couple of examples then of some of the kind of work we're doing. In this case, this is some work done by Randy Persaud, who is a graduate student. And in this case here, we want to understand properties of metal clusters. And we looked at copper and silver and gold clusters And what we found then with looking at gold clusters is that in order to get realistic numbers that approach the correct cohesive energy for the bulk, we had to include spin orbit corrections into gold. Okay, and why do we have to do that? Because gold is a heavy element, even though it shouldn't you wouldn't think it would have spin orbit because it has a outer s orbital occupied only is a singly, there's an ns orbital that's occupied by one electron, and that would be spherically symmetric. There is a spin orbit correction, and if we want to get a good result, we actually have to include a correction for spin orbit effects. And we do that, then we get within about 2 kcals per mole of the bulk cohesive energy, whereas with copper and silver, we get within better than 1 kcal without any spin orbit correction. So gold is a tricky system to do, and these are not tiny corrections by the time we get to the larger systems. As another example, let's go ahead and look at the energetics of CO2 minus in aqueous solution. What we wanted to do was to predict the reduction potential for CO2 to CO2 minus. We get a value of, versus the standard hydrogen electrode, we get a value of about minus 1.93 electron volts versus experimental values of minus 1.9. Why is this interesting? Because you actually have to put CO2 in water to trap an electron because it does not do it in the gas phase. Well, we did though use a correct kind of water cluster approximation for the gas phase and solution, and then did a self-consistent reaction field to treat the far field effects. We were able to get very good values for the electron affinity of CO2, which is important in geological chemistry as well as in catalysis. And we're also then able to understand about how the electrons can be attached and desorbed. And we find then that the vertical detachment energy involving a major rearrangement of the CO2. That's to take the electron off the CO2 in solution because it's very bent, has a very large value, almost double the value of the adiabatic electron affinity. We've also been trying to understand how nanoparticles form. And so in this case, we've been using machine learning approaches to develop structure energy relationships. In this case, we're going to be looking at how we can use fragment recognition schemes to develop reliable prediction of the properties of nanoparticles. And do this by using a small training set and then get to a much larger one, and then we can actually then go ahead and explain the growth mechanism for zinc oxide clusters, and then leading to nanoparticles, nanocrystals, and then actually into bulk crystals. We can then do this, and we can then get various kind of morphologies and explain the basic structure growth for something like zinc oxide. We've also applied this to more complicated systems like calcium carbonate and so forth. Coming back to another example, we're able then to do the same thing we did before. We're able then to predict the redox couple for the H dot to H minus redox couple. Here we find this is about minus 0.03 electron volts. And we did it using the same method we used for the CO2. Why is this interesting? Because this number is not established. Can't make hydride ion in water. Well, you can make it, but nobody's ever observed it. And so this scale then is really not well known. We need to know the absolute value for this so we can develop relative hydricity scales that can then be put on an absolute basis. And we need the absolute value for the redox couple for H and H minus. And we do this again using a super molecular plus continuum approach. As another example, we've been interested in the stability of ANO2, where AN is an actinide. In this case, this is a very common ion that shows up in much of actinide chemistry, especially for things for uranium, plutonium, and so forth. But we want to go beyond that. We want to go to the heavier ones and see what's going to happen. And what we find then is that we might then be able to make this kind of species for berkelium, and also for curium, and maybe for americium, if we have the right kind of ligands. But otherwise, we probably can't. For something like californium, then we probably can't make these kinds of quantities, no matter what we're going to be doing. And this then basically, lets us enable us to understand why we can have the +6 oxidation state early in the actinide series, but it moves over then to the +2 and the +3 later on when you go past plutonium. So in this case here, we're really trying to understand what's going on in these actinide species, and what we find then is rather than getting the structure on the upper right, you get all different kinds of structures we have to worry about. Is it O2? Is it O2 minus? Is it bent? Is it linear? And we've been able to understand a lot of what's going on, and then we can actually then look at experiments with John Gibson at Lawrence Berkeley National Lab to establish what these structures are. In another case, working with John, we've been looking at the stability of things like protactinium, okay, or in the actinides, or praseodymium in the lanthanides. And what we find looking at their oxides is that protactinium basically looks like a transition metal, whereas the praseodymium looks more like a lanthanide or like an actinide kind of species. And we did this by comparing the hydrolysis chemistry of these species experimentally and computationally to the same thing for the transition metals, and we can show them that protactinium behaves very much like a transition metal, just as thorium does. Okay, and I think I'll go ahead and just end here by showing the kind of techniques we use to do these calculations. We use what's called the FPD method. This is a method developed with Dave Feller and Kirk Peterson and myself, where we look at large-scale coupled cluster calculations extrapolated to the complete basis set limit. We include all kinds of other corrections, including core corrections, scalar relativistic corrections, spin orbit corrections, zero-point energies, and all the other little things we need to do in thermodynamics to make reliable predictions. And our goal here, again, is to get our chemical accuracy. Thanks for listening, and I hope you enjoy yourself and that you'll be coming to the University of Alabama as a grad student. Take care.